Welcome back. This video is for you if you're all about wondering why do certain series tests for convergence and divergence work. So if you're just curious, why does the integral test work? Let me show you. So first things first, we're going to start out with an example of the sum of 1 over n, where n equals 1. It's the perfect one to use with the integral test. We're going to start out with understanding why things need to be continuous, decreasing, and positive. So let's go through that list. Continuous. You've got to have a continuous curve to use the integral test because if it's not continuous, you can't integrate. So you've got to be continuous on the interval. Number 2, you've got to be positive because the test is trying to eliminate that squirrelishness or the weirdness that comes if the if the series alternates, I should say. So we make it all positive. If there was a negative sign here, we would just factor it out. And then why does it have to be decreasing? Because if a curve continuously increased, well, the series is going to diverge, like almost immediately, right? You're going to have an infinite integral that we're taking here. For an increasing function, that area is going to be way more than, well, a finite number. It's going to be infinity. So that's the reason why we're positive, continuous, and decreasing. But why does the test work? So we've already seen the test work, and if you haven't gone over that process, please check out video 1 in this lesson. But assuming that you have seen it, we're going to expand this out. This is 1 plus 1 over 2 plus 1 over 3. This is our harmonic series, very powerful series. Plus, and it keeps on going on to 1 over n, and it doesn't stop. So we've actually already looked at a series like this one before, and we saw that this thing actually does diverge. But we're going to see why. So what the trick here is that we're going to take these values and look at them as areas of rectangles, like a Riemann sum, essentially. And so if we look at the Riemann sum with left-hand approximations, if you take a look at the area of this first rectangle right here, that area is 1. So that's the first term in your series. Then we take the next left-hand approximation, right, down to 3. And that area is not 1, but 1/2. Right? It's got a height of 1/2, and then it's got a width of 1. So that's an area of 1/2. And then here, we're going to take the height at x equals 3 to 4. That's a width of 1 and a height of 1/3, 1 over 3, right? This is the function, by the way, of 1 over x. And so that would be 1/3. And then we'll go to 1/4 and we'll stop this madness. But what you should notice is the area of each rectangle is equal to each term corresponds 1 to 1 with each term in the series, and so on. And it keeps going on and on like that, infinitely much. So what we should also see is that the left-hand Riemann sum, so I'll say the left-hand R sum, is greater than or equal to the true area from 1 to infinity. So what that means is our series, which is that left-hand sum, n equals 1 to infinity of 1 over n, that is the left-hand sum, that's what we just showed, is greater than or equal to the true area would be the improper integral from 1 to infinity of 1 over x dx. That would represent the true area here. And what I'll do there, I guess, is I'll shade that in here. So that's all of this area all in here, all the way down. Right, so that's the true area. But we see that our rectangles overshoot that true area. And what we've already shown, and I'm not going to show the algebra for it, we've already shown that this integral actually diverges. So that means that we are greater than or equal to a diverging amount. So a diverging amount. In fact, this thing goes to infinity. And what's greater than or equal to a diverging amount? Well, a diverging amount. So that means that our series has to diverge. Isn't that cool? That's why it works. So let's go into now one that converges. So what about a converging example? Now we haven't looked at 1 over n squared, so I took 1 over x squared as f of x to describe that. And now what we're going to do is see, as we expand this out, a similar idea with rectangles. So 1 over 1 squared is 1, plus 1 over 2 squared is 1/4, plus 1 over 3 squared is 1/9, plus 1 over 4 squared is 1/16, and so on and so forth. Now note again that we've got continuous values from 1 to infinity on this function. As we see on this function, from 1 to infinity, it's continuous. It is above the x-axis, it's positive, and it's decreasing the entire time. So what I'm going to do here, instead of using left-hand sums, I'm going to use right-hand sums. Why? Because we could have done that on the last one too. A right-hand sum would have been an under approximation, but An under approximation being less than diverging doesn't show us anything. Being more than diverging does. So I suspect that this integral is going to actually converge. So I want to be under converging. So I use a right-hand sum to represent the areas of things. And you might be like, well, what about that one value there? So what I'm going to do is I'm going to say that this is equal to, well, 1 plus, where's that 1 going to come in? You'll see in a second, but this is your 1/4 right here. This is your 1/9, right? Because we're at 3 squared, so that's 1/9. I can barely fit that one in. And then this one right here will end there. All under approximations is your 1/16. So yet again, the areas of each rectangle represent the individual terms here. Where's the area 1? I mean, we can draw it in here, but that's technically the integral then from 0 on. So I'm not going to include that. So what I now know is that the right-hand sum plus 1, so 1 plus the right-hand sum is going to be less than or equal to the true area. What's the true area? Let me highlight that one again. Let me show you. The true area is all up in here. So it's this entire value. Oh, and it gets smaller and smaller and smaller. And it goes on and on and on forever. So we see that those rectangles and their areas are all undershots. And well, and I would say it's less than or equal to the true area plus 1, right? We technically should have the 1 there if we're really showing it. And so what does that mean? Well, that means that we would have that this is less than or equal to the true area, which is the integral from 1 to infinity of 1 over x squared dx plus 1. And again, the plus 1 there is because we don't have that 1 that we included in the Riemann sum. So you've got 1 plus the right-hand sum, so that would be the same as the exact series. So the exact series of 1 over n squared is less than or equal to this. Well, that's less than or equal to that. This, by the way, when you solve it out, we've actually done this in our previous chapter. I'm just going to say it converges. If you have trouble doing that, go back to chapter 8. It converges. So it's less than or equal to converges plus 1. And a converging number plus 1 converges. Oh. So, therefore, the series itself also converges. So what I'm showing you is we've got that one-to-one relationship that if we've got a positive, continuous, and decreasing function that we're taking the series of, and that function fits all those bills and converges, then so does the series. If it diverges, then so does the series. And this actually points out why just because an infinite integral converges to a certain value doesn't mean that that value, that area that's in the yellow here, is equal to the series, because we can see that the series values are all those rectangles, which is not equivalent to the actual area. So be careful there. We don't find the sum of the series here when we get a converging answer. We just find that the sum also converges. That's it, y'all. Riemann sums in all its glory. You know I love it. I can't wait to see you in the next video where we go over something that is very important but very simple. It comes from the integral test known as the P-series. I'll see you there, but until then, peace.